Today we're going to talk about monotone sequences. Let's recap some ideas from before. Say that F is a complete ordered field and that we have a sequence, that is, a collection of elements x sub n in F, which are indexed by some natural numbers n. Here we assume that n is an integer greater than or equal to 0. We make a few definitions for the sequence. First, we'll say that this sequence converges to an element L if, given any positive epsilon, we can find a delta such that, in absolute value, xn minus L is less than epsilon whenever n is greater than delta. In this case, we'll say that xn tends to L, or that the limit as n increases without bound of xn equals L. We'll say that the sequence increases without bound if, for every positive epsilon, we can find a delta such that xn is greater than epsilon whenever n is greater than delta. The idea here is that we'll think of xn as going to infinity. Similarly, we'll say that our sequence decreases without bound if, for any given positive epsilon, we can find a delta such that xn is less than negative epsilon whenever n is greater than delta. We can think of xn as going to negative infinity. In either of these cases, we'll say that our sequence diverges. Finally, we'll say that our sequence does not converge if it neither converges nor diverges. We found a couple of examples last time. Say that we have a geometric sequence, an arithmetic sequence. That is, our xn looks like x0 plus n times b for some non-zero number b. In this case, we prove that our sequence diverges. That is, the sequence increases without bound if b is positive, and it decreases without bound if b is negative. Similarly, we found a sequence that looks like it's coming from a geometric sequence. Here, let's define xn as L plus x0 minus L times rho to the n, where rho is a number here between 0 and 1. We proved that this sequence converges to our limit L. If you recall, we were able to prove this in the case when f is the real numbers, although today we're going to try to write down a slightly different proof, assuming that f is simply any complete ordered field. Before we get into things today, I'd like to give an aside to discuss why have we made these three weird definitions. That is, that we have a sequence that converges, a sequence that diverges, and then we'll say that our sequence does neither. So, can we really make a unified definition when we simply use the phrase does not converge? That is, can we really say that in a sense, converging and diverging are almost the same thing? As a motivating question, say that we have a sequence of numbers in F. Remember that we really have three possibilities. Either our sequence tends to a number L, our sequence increases without bound, or our sequence decreases without bound. Is there a way to unify all of this into one coherent definition just to say that our sequence converges? In order to answer this, let's think of our field F in a different way. What we're going to do here is we're going to think of the elements in F as points on the unit circle. Intuitively here, we can think of F as being a number line, and somehow we're trying to wrap the number line up so that all of the points are in a nice circle. Notice that if we go either infinitely far to the left, we approach negative infinity, and if we go infinitely far to the right, we approach positive infinity. Somehow those should kind of wrap up to be one point at the top. We can try to make that a little bit more explicit with the picture here. Again, as we move to the right, we see how the point moves very close to the top of the circle, and if we go to the left, we see how the point goes very close to the top of the circle again. This is the idea of saying that we actually do have things wrapped around to be on the unit circle. In this way, we're going to think of an element t in F as a point P on the circle. So, what does it mean to say that we have two numbers that are very close to each other, namely a Tn and a Tm? Since we have points in the circle, we can talk about the distance between them, that is the Euclidean distance. So, using the formula that you see here on the slide, we can see that these 2 points, Pm and Pn, are very close to each other precisely when Tm and Tn, as numbers in F, are very close to each other. What about this plus or minus infinity? Well, as we saw from the previous slide, plus or minus infinity really should correspond to the North Pole on the circle. In particular, let's take a look at the Euclidean distance between a point Pn on the unit circle and the North Pole n, which is simply 0, 1. We'll see that the Euclidean distance between the two, now we can write in terms of 1 over Tn. So in other words, if Tn is very large, that is if it's approaching plus or minus infinity, then we see that our Euclidean distance, P sub n minus capital N, is very small. Using both of these, now we have a nice coherent definition. We can say that our sequence A, which consists of T0, T1, T2, and so forth, converges if, given any positive epsilon, we can find a delta such that Pm and Pn are close, epsilon close, whenever m and n are large, that is, they're both greater than delta. We'll say that our sequence A does not converge otherwise. We're going to come back and talk about this construction later on in the course. But for now, let's talk about the idea of monotone sequences. As a motivation, remember this example that we discussed in the last lesson. Say that we have a sequence defined here, x sub n is L plus x0 minus L times rho to the n. We proved before that this sequence converges to L when rho is between 0 and 1, but unfortunately our proof really only worked when our ground field F is the real numbers. This is because in order to construct the proof, we had to look at a delta, which we defined as a function of epsilon in terms of logarithms. Let's maybe review some parts of that proof now. Our proof really relied on the following identity. That is that the absolute value of xn minus L looks like the absolute value of x0 minus L times rho to the n. The idea of how we constructed our delta was to say that we can always choose a natural number n large enough so that rho to the n is very small. So the question is, can we do this whenever we have any complete ordered field F? Well, the idea is that as long as rho is between 0 and 1, then rho to the n plus 1 is less than rho to the n. So the idea is that we have a sequence that is decreasing. Our sequence gets smaller and smaller and smaller. So yes, we do expect to be able to find an n, so this works for any complete ordered field. Using this motivation, let's make the following very general definition. Say that we have a complete ordered field F, and let's say that A is a sequence consisting of T0, T1, T2, and so forth. We'll say that our sequence is monotone increasing if T sub n plus 1 is greater than or equal to T sub n. We'll say that our sequence is monotone decreasing if T sub n plus 1 is less than T sub n. We'll simply say that our sequence is monotone if it is either monotone increasing or monotone decreasing. Here's our main result. Again, say that we have a complete order field and a sequence A. Let's say for the moment that A is monotone increasing. If A has an upper bound, then the sequence converges. If A does not have an upper bound, then the sequence increases without bound. Similarly, let's say that A is monotone decreasing. If A has an upper bound, then again the sequence converges. If A does not have an upper bound, then the sequence decreases without bound. Let's discuss the proofs of these. First, let's assume that A is a monotone increasing sequence. Remember that we have two possibilities. A could have an upper bound or it could not. If it does have an upper bound, we need to show that our sequence x sub n tends to a limit L. Well, we're dealing with a complete ordered field, and A is a set. If it's non-empty and has an upper bound, then it must have a least upper bound, which we'll call capital L. We're going to show that our L here is our limit. To do so, let's let epsilon positive be given. Since L is the least upper bound, we found before that we can always find a delta such that x delta, an element of the sequence A, is as close to L as we would like for it to be. That is, there's a number delta such that x sub delta plus epsilon is greater than L. Now, choose any natural number n greater than delta. We can see that in absolute value, xn minus L is actually equal to L minus xn. Well, this is because L minus xn is positive, since L is an upper bound. But now we have a monotone increasing sequence, so as long as n is greater than delta, xn is greater than x delta. So, flipping things around with the negative sign, we see that this absolute value is less than or equal to L minus x delta. Now, according to the statement about how x delta was chosen, we see that this difference is less than epsilon. Hence, we've shown that whenever n is greater than delta, in absolute value, xn minus L is less than epsilon. This means that our sequence A does indeed converge to L. On the other hand, let's say that A does not have an upper bound. Of course, we need to show that the sequence increases without bound. To this effect, let's let epsilon positive be given. We know that we can find a delta such that x delta is greater than epsilon, otherwise A would have an upper bound. Now, we have an increasing sequence, so whenever n is greater than delta, x sub n is greater than x sub delta, which means that xn is greater than epsilon. This is exactly what it means, however, for the sequence to increase without bound. Now we can show the second statement about decreasing sequences. This proof is almost the same. Now we just simply replace supremum with infimum, and the proof pretty much works almost the same way. There's just a few minor sign changes. If A does not have an upper bound, then pretty much we can go through the exact same argument. Now we just have to flip around the sign, and instead of looking at x delta greater than epsilon, we need to say that x delta is less than epsilon. It's less than negative epsilon. And again, the proof works out almost the same way. Let's end by discussing a few examples. First, let's return to our sequence corresponding to an arithmetic progression. That is, x sub n is x0 plus nb for some non-zero element b. Well, by looking at the difference, xn plus 1 minus xn, we see that either we have an increasing sequence or a decreasing sequence, depending on whether b is positive or negative. Hence, we have a monotone sequence whenever b is non-zero. But we've also seen that this sequence diverges. That is, in this case, we have monotone sequence that is not bounded. As another example, let's go back to the one corresponding to a geometric sequence. That is, x sub n is L plus x0 minus L times rho to the n, where rho is between 0 and 1. Can we actually use some of these ideas to prove that our sequence converges to L? What we're going to do is write a new sequence, t sub n, which is the absolute value of xn minus L. Notice in this case that by simply working through the formulas, we find that this is the absolute value of t0 minus L times rho to the n. In particular, tn plus 1 is rho times tn, so that we actually have a monotone decreasing sequence. In fact, we know that the sequence has a lower bound, which means that now we have a sequence that is bounded. Again, our sequence here corresponds to the T sub n. In this case, the monotone convergence theorem asserts that T sub n tends to 0, since 0 is the infimum of the set, that is the greatest lower bound. In particular, given a positive epsilon, there must exist a delta such that Tn is less than epsilon whenever n is greater than delta. But now, substituting back in our choice for Tn, we find that the absolute value of xn minus L must be less than epsilon whenever n is greater than delta. But now, we've just found a brand new proof to show that our xn does tend to L, and now this proof works for any complete ordered field. We no longer need to introduce logarithms to get our proof to work. Thanks very much for watching.